Alexopoulos. I'm working at the MRC Biostatistics unit of the University of Cambridge as research associate, and I'm going to speak to you about Bayesian real-time epidemic monitoring of COVID-19. So this is a project with several collaborators and is mainly led by Daniela Angelos from the MRC Biostatistics unit of the University of Cambridge. So you can see my slides changing, right? Yeah. Are you hearing me?
Yes.
Yeah. Thank you. Okay. So I will start with a brief introduction on the problems. I will talk about epidemic modeling of COVID-19. I will speak about the Bayesian methods that we use to conduct Bayesian inference for the epidemic model. I will give you briefly some of our real data results, and I will close with a small discussion about mainly ongoing work. So, real-time epidemic monitoring, why it is important. So it is known that disease outbreaks place significant burden on healthcare systems, and thus prompt public healthcare response is necessary because we need to bring things to assist the healthcare systems to come back to normality and help them to deal with this burden due to the epidemic or the pandemic. So to deal with these two issues, we need to monitor and to predict any epidemic or epidemic, the evolution of epidemic or epidemic in real time as the data accumulate. So why it is difficult? It is difficult because we don't have direct data on new infections, and thus we need to rely on noisy and incomplete surveillance data, which are usually coming from multiple sources and often are biased, okay, in this sense. Also, some behavior changes can affect the data, can alter the true dynamics and the reporting patterns. And last but not least, any analysis has to be carried out in a timely fashion, right? So our group, the last 2 years, needs to estimate the model, the parameters, and run the algorithms 2 or 3 times every week by using the latest available data and produce results in order to inform several government committees about the evolution of the pandemic in the UK. And all this has to happen within a few hours. So we cannot wait for days or weeks to estimate the model. Okay. And now, why we choose to be Bayesian? So we need to, first of all, we need to handle efficiently the uncertainty, and more precisely, any uncertainty coming from the different sources that we have for the data, right? So we have different sources, multiple sources for the data, and Bayesian methods are very, very well designed in order to deal with this type of data. Moreover, under the Bayesian paradigm, we can produce prediction intervals, we can estimate functions of epidemiological interest quite easily. So these are quantities that are readily available, like the reproduction credible intervals or prediction intervals for reproduction numbers. And then we can also deal efficiently with mathematical challenges imposed from this type of models. So epidemic models are compartmental models describing the flows between the different disease compartments, and rely, in order to do this description, they rely on the solution of a system of dynamical equations. Now, this system of dynamical equations may have some inherent features which, combined with the fact that we have data from multiple sources, open biased and so on, this can result in a significant statistical challenge, which is the likelihood not identifiability, which is a very, very important challenge and very important issue when you want to make statistical inference. Okay, so Bayesian statistics can utilize prior information and construct prior distributions in order to overcome likelihood identifiability problems by using probability theory properly. Okay, so so let me go now to epidemic, to our model for COVID-19. Okay, So our point of departure, our base model, is this deterministic SEIR model, which is consisted of 4 compartments, of 4 states. We have the susceptible individuals, we have exposed individuals, we have infectious individuals, and we have removed individuals. Actually, we have 2 states for the exposed and the infectious to allow for a bit more flexibility and restrict some assumptions from the similar model. So each compartment is described the state of the disease for the Rth region of the country, for the TK time point, and for the ith age group. So we have capital R regions where we have separated the country, the UK, England actually. We have capital K time points where we study the pandemic, and we have capital A age groups. Okay, so you can see that this is a discretized, actually, dynamic system, continuous dynamic system, but has a time discretization and describes the flows between the compartments. Okay, so this system depends on some parameters, which are the mean infectious period. This DI parameter is the mean latent period, which we keep DL, which we keep as fixed during our study. And we have this lambda parameter, which is the rate on which susceptible individuals become infectious individuals. Okay, and we have also this delta here, which is related to the time discretization of the continuous time system. Okay, so according to this SEIR model, we have new infectious generated according to this equation here, where you can see that this depends on the compartments of the model and depends also on this parameter B, Rij, where this B is a probability, and this is a probability of infection for someone in the age group I by someone in the age group J at time point Tk and region R, and this probability is given from this formula. Now, this formula depends on these matrices C, where these matrices account for conducts between individuals of different age groups. Also, this probability depends on this reproduction number, this R0, which is the number of secondary infections caused by primary infection in a fully susceptible population, and is also a function of some parameters. There is also this dominant eigenvalue as a normalizing constant here. And importantly, we have also a parameter beta here, which I have emphasized by red, in red font. And this parameter beta, I'm going to speak a bit more about this. This is, we call this as a transmissibility parameter, and we see this parameter as a chance to introduce some stochasticity in our deterministic model and account for unobserved events during the infectious process. Okay, so we model this, the logarithm of this parameter, as a random walk process, as a stochastic random walk process. More precisely, we do it as a piecewise constant process, which change states fortnightly to keep the dimension of the model low as the pandemic evolves over time. And this is our model, our stochastic model for this transmissibility parameter, which allows some randomness in our deterministic model. Now, what I described is a simple SIR model, or a bit more complicated, but is a model in an early stage, right? This is the model that we used actually in the early stage of the pandemic. Now we have a bit more complicated model because we need to account for vaccination effects. So you see that our model is flexible enough to get updated with several pandemic characteristics. So now we have this model here where you can see how susceptible and exposed and infectious individuals are affected from vaccination and how they transfer across the system. We're also working to further develop this model to account for waning immunity from vaccines and from natural immunity. Okay, so this is our main model now. And let me briefly speak about our data sources to inform this model and estimate our parameters. So we have time series data. We have time series of deaths, of counts of deaths from the beginning of the pandemic up to now. We have time series of serological data as the proportion of positive tests, serologically tests, where they inform us about the immunity, about people that have get infected because they count the antibodies in the blood. Importantly, we have some data about prevalence, but unfortunately, due to sensitivity restrictions, we cannot have the observed data, the direct data, because these are within the Office of National Statistics and cannot be transferred outside of that. So we can export, however, some time series of estimates from a protected environment. And then again, since we are having a Bayesian application, we are using Bayesian methods. There are methods for including this type of estimates as data in our model, and this is called Bayesian melding, and you can see more details on this paper if you are interested. Then we have some other, we call them explanatory data because they don't go directly in the likelihood of the model. You can think them as covariates in a regression type model, which are the conduct matrices, for which I already have spoken briefly, which describe rates between conducts for different age groups. These data are coming from several studies, from the Polymod study, from Google Mobility, and from all these studies. And we also have explanatory data on vaccinations. Okay. So let me also give you briefly the likelihoods for our observed and estimated data. So we have a negative binomial likelihood for the deaths, which has a mean that depends on the infections generated from the model. We have a binomial likelihood for our serological data, which depends again on the susceptible individuals and on the parameters of the test, the sensitivity and the specificity of the serological tests. And we also have a model for our estimates for the prevalence due to the restrictions that I described before. Okay, so all this model and likelihoods depend on parameters, and these are our parameters. So we have a set of parameters that change across regions, and we call them region specific. We have a set of parameters which are common across the regions, and we call them global parameters. And we also have a set of dynamic parameters, right? The parameters of the random walk process, the states of the random walk process, which change over time. So we have also an increasing dimension there. Okay. And now, since I have described the model, I have described the parameters, let me speak about how we conduct Bayesian inference about the model and the parameters. Okay, so if we think as all the data in the model in the process, and you also can imagine that we use very informative priors for the majority of the parameters, and this allows us to deal with problems such as identifiability that I mentioned in the beginning that usually appears in epidemic applications. Then we can write down our posterior distribution, which is the product of the priors and of the likelihood, which is highly intractable in our case. And then we have to note also that it's a very high dimensional problem, quite high dimensional problem with more than 500 parameters currently in the model. So if we want to conduct Bayesian inference, we need to design sophisticated Bayesian computational methods, okay, in order to produce results on time. So we have also to note that usually these sophisticated Bayesian methods have to depend on gradient information from the likelihood in order to be efficient. But in our case, we have to note that we have to restrict ourselves in a situation where we don't always have tractable derivatives of the likelihood, right? So it is not so obvious how to design sophisticated Bayesian computational methods. However, we design a Markov chain Monte Carlo algorithm to conduct Bayesian inference, which the main scheme is described from this algorithm here. So you can see that we have a different block in our MCMC to draw samples for the regional parameters and a separate block from the global parameters. So we have R+1 blocks. In each block, we are using adaptive MCMC to draw the desired sums. Importantly, for this loop here, we can implement it in parallel, so we can save a lot of computational time. And let me also a bit zoom in the adaptive procedure that we use, because this is important for us in order to have results on time. For now, you can imagine that we have a block where we denote the parameters in this block with X. So if is the global block, X is equal to theta. If it is the regional block, X is this vector here. So, and Xi is the value of the parameters in the ith iteration of the MCMC algorithm. So usually in adaptive MCMC, you propose some values from for your parameters from this Gaussian proposal distribution, and then you accept or reject them by using the usual Metropolis-Hastings probability. Okay, so why it is adaptive? It is adaptive because you are trying during the MCMC algorithm to learn your parameters of your proposal distribution, these covariance metrics. And here we use this idea of Christoph Andrew, which is a well-known paper in Bayesian statistics about adaptive MCMC, where you can learn the covariance matrix by using Robbins-Monroe recursions, and you can also keep a desired acceptance rate for your application, which is usually 24% or something like that. However, you need to be careful here because the variations of your proposal parameters, of the parameters that you learn, has to vanish with respect to MCMC iterations in adaptive MCMC methods, because this vanishing adaptation is crucial for the ergodicity of the algorithm. So it's crucial in order to keep targeting the right stationary distribution for your Markov chain. But trying to keep this vanishing adaptation property, you can tune your proposal parameters to bad values, and then you can have a Markov chain Monte Carlo that needs a long time in order to converge. Recently, we had such chains. So we had chains where sticky chains cannot move, cannot explore the parameter space well. And you see that we had a large amount of iterations. We have invested a lot of computational time to run the model. However, we couldn't tune well the parameters of our proposal distribution, and we didn't manage to explore the space. So we needed to improve on that. In order to improve on that, we noticed that the Robbins-Monroe recursions aim to find the roots of this equation here, where you have alpha star, your acceptance desired, your desired acceptance rate. S lambda sigma here is the average acceptance ratio of your Markov chain, of your algorithm. And we noticed that we may a source of bad values for lambda and sigma for the proposal parameters can be the overfitting, the type of overfitting, let's say, when you are trying to find the roots of this numerically of this system. So we suggested to prevent overfitting by borrowing some ideas from machine learning applications. So in particular, this early stopping regularization. And to perform that, we designed these 3 steps. So we calculate the average acceptance ratio, the sample average acceptance ratio based on batches of m consecutive MCMC samples. We check then if our average acceptance ratio is within a desired range. If it is, we don't perform anymore the Robbins-Monroe recursion, so we save ourselves from our overfitting. And to be even more sure and prevent any loss of ergodicity of the chain, we stop since we have obtained a desired acceptance rate, we stop the Robbins-Monroe recursions, we adapt our proposal distribution after the burn-in period. And then we managed to explore the space, which is crucial for Bayesian applications, because if you don't have explored your parameter space, you don't have reliable estimates of your pandemic. And then we managed to explore well. Still, we have to run our sampler for quite a lot of iterations. So this is something that we need to improve. But at least now we have reliable results again.
Angelos, sorry, you've got about 2 minutes left.
Yeah, so I'm very close to finish. And just to mention that all this leads to real data analysis and the real data results, where, as I said, we use them to advise the government. Here are snapshots of our results published also in our websites. Here are our estimates for the reproduction numbers from last week. We estimate the number of infections, daily infections, cumulative infections. So if you go in our website, you can see how our model fits the death data, for example, and many other plots. And let me close very quickly with ongoing work, which is separated into 2 directions. We have work on Bayesian inference, on improving our inference, and on modeling development. So we would like to construct a unified MCMC framework that can account for these characteristics, so can identify possible multiple modes caused from non-identifiability that we discussed at the beginning. We can have an MCMC that jumps between different modes, take into account the increasing dimension of the problem, have a nice optimal proposal distribution, but with a reduced number of iterations, not 1 million as we saw before. And then we also develop our model to account for immunity from vaccines, natural infection, and we would like also to use multiple data streams in order to conduct inference like hospitalizations and deaths and so on. So that's it. Thank you very much.
So first of all, do we have any questions from Angelos from the floor? Any on Jane? Are there any? Okay. Well, while if people are having a think, I might just ask you a quick question, Angelos. So you're saying that you so like the developments for the model, so looking to account for waning immunity and vaccines and natural infection. So what are you going to fit the parameters for things like waning immunity, vaccines and natural infection? Are you looking to try and use some specific data sources? So I just was wondering what your kind of plans for that were.
Yeah, so one thing is that this thing of including more data streams is required for this process of trying to inform the model for immunity. So from hospitalizations, we can get informed for a while for the infectious process, how it is, the admissions are reduced or increased or decreased. And also we can include our vaccination data in the likelihoods, right? Because as I saw you before, we have some explanatory data for the time being that we use as covariates, let's say, in the model. So we would like to include them in the likelihoods in order to inform the parameters of the model with respect to vaccinations.
So if there are, oh, there's one question.
Hi, I'm Tim Russell from London School of Hygiene and Tropical Medicine. I was just wondering how your slightly like bespoke MCMC methods compare to the more standard ways of dealing with like bi or trimodality, like parallel tempering, and then your root solving method for getting an optimal proposal step. How does that compare to like HMC, which is sort of the more standard methods that I know about anyway? Thank you.
Yeah, also it's a very nice question. Thank you. So yes, tempering could be a very nice alternative for inference for this work, but there are two main drawbacks for tempering. So you see, as I said, that this is a high dimensional problem, right? So we have at least 500 parameters now, and it's getting increased with respect to time because we have a dynamic random walk process there. In order to manage to conduct inference, we split this in different blocks to reduce the dimensionality of each block. And tempering appears to scale exponentially badly with dimensionality, right? So I'm not sure how well it would perform with such high dimensions. There are appearing some papers in the very recent literature that try to deal with high dimensional tempering applications, but then these depend again on gradient information from the model. Actually, they depend not even on first order gradients, but second order gradients of the derivatives. And since we don't have this in explicit form, let's say, it's not very easy to follow this literature, or would be computational even more expensive to do it. So this is for tempering. And then for HMC, again, there you need derivatives, you need second order derivatives, you need to have your proposal covariance matrix to be state dependent, let's say. So this is, except from the fact that we don't have the derivatives will be even more computationally expensive for us. So we need to solve our problems without increasing the computational complexity of the algorithm.
And I think that brings us to time. So thank you again, Angelos, for a really great talk.
Thank you very much.
So our last speaker of today's session is here in person, which is very nice. So we've got Derek Groen from Brunel University of London. So he's going to be talking about